Okay, so this next video is going to be a video on velocity time graphs. So before we start getting into velocity time graphs, I want to start just by a quick recap of position time or distance time graphs. So take a look at the screen here at the top. You are going to see, or you will see, 3 distance or displacement time graphs. So what I want you to do is take a look at those and think about what each of those graphs means. Like what kind of motion would it be representing? So if I take a look at this first one on the left, I have a displacement time graph that has a nice slope up and to the right. So make sure you're writing these down. I want to see all 3 sketches in your notebooklet, and then underneath that, what do you think is happening? So if I have an object that's traveling in a nice flat line like that, that actually means it's traveling at a constant velocity. So I have a nice straight line, it's traveling at a constant velocity, meaning the displacement will change in equal amounts over equal time periods. I could take that line, now take a look at the one in the middle. The one in the middle is showing me now kind of what we call a curved line, or in math that might be an exponential increase. What that means is the velocity is increasing. Remember back from a few videos, if your velocity is increasing, that is called positive acceleration. The one on the right kind of shows the opposite. I have a curve that kind of gets less and less steep as you go through the situation, kind of up here, which means an object is slowing down, or that's negative acceleration. So I can put these 3 answers in here. So what I want to see in your notebooklet is all 3 graphs drawn and then describing what they mean. So the first one, again, constant velocity. The middle one, it's accelerating, or its velocity is increasing. Those 2 mean the same thing. And the one on the right, it's decelerating, or its velocity is decreasing. So those hopefully are pretty straightforward. Now I could take those and show or draw you the corresponding velocity time graph, or a velocity time graph that matches the position time graph. So underneath that, I want you to draw these 3 graphs, and then we'll talk about why they mean the same thing. The first one, constant velocity. If I have a velocity, I don't have numbers on my axes here, but you can imagine I could put it, this could be 0, 2, 4, 6, 8. Let's say this is at 5. This is showing a constant velocity because this whole entire time, all the way through here, this object is staying at exactly 5 meters per second. And if I'm staying at 5 meters per second, my velocity is constant. Now, this one in the middle, something pretty interesting happening. If I have acceleration, that really means my velocity is increasing. So right here at the beginning, I could have a velocity that would be like 0 or something. Then 2, 4, 6, 8, all the way up. So that is showing me a velocity that's increasing. The last one, if I want to show deceleration, or a velocity that's decreasing, is just the opposite. I want to slope that down. So these kind of show you how I can take a position time graph and match it to a velocity time graph like that. So make sure you have this written down. Okay, we've been doing some work with slope. We're going to continue with that on a velocity time graph. So this question, what does the slope of a velocity time graph tell you? Well, I know that slope is rise over run. In this case, my rise is a change in velocity because that's what's on my y-axis, and a change, or my x-axis, is a change in time. So I end up with a formula that says a change in velocity over change in time, or v2 minus v1 over t2 minus t1. Again, this formula looks familiar. Change in v over change in t is the same thing as calculating acceleration. So the slope of a velocity time graph gives you acceleration, which is what it says in that box on the bottom right-hand side. Okay, so let's take a look at an example. Here I have a graph. It's a velocity time graph. So now, since I have 2 different types of graphs, my very first step is always going to be to take a look at what kind of graph is this talking about. Because if it's a position time graph, I'll answer the question differently than if it's a velocity time graph. So this one's a velocity time graph. So this question says, describe the motion of the object between 0 and 4, and then between 4 and 10. So I'm going to call that section A of the graph, and we'll call that section B of the graph. So think about this for a second. Section A of the graph, like we just talked about, shows me a nice straight line upwards. So section A means if I have a straight line slanting up on a velocity time graph, that means it's acceleration. So A is showing me acceleration. Section B here, between 4 and 10, is a flat line. There's no slope, or the slope is 0, because it's straight across, which on a velocity time graph means constant velocity. So if I have a straight line like A, it's accelerating, if it's sloping up like A. If B, it's straight across, that means it's a constant velocity. So now, same graph, this question actually asks me to calculate acceleration. So let's do this one. Section A, I'm going to start with the formula. Acceleration is a change in velocity over change in time. So I have acceleration as change in velocity over change in time. My section A, I have 0, 0, and 8, and 4. So I can say my change in velocity is final velocity minus initial velocity. My final velocity up here at the top is 8. Velocity is measured in meters per second. My initial velocity, it started at 0, again, meters per second. On the bottom of this equation, I have a final time of 4 seconds and an initial time of 0 seconds. So in this, I end up with an 8 on the top and a 4 on the bottom. 8 divided by 4 gives me 2. My units, really important. I have a meters per second on the top. Meters per second on the top, seconds on the bottom, gives me a unit of a meter per second squared. Okay, same thing. Now for section B. This one's a little bit easier. I don't actually even need to do anything for it because I know that at the beginning of section B right here, I started at a velocity of 8. But at the end of the section, I also had a velocity of 8. So my velocity stays at 8. I end up with an acceleration of 0. I could prove that also because 8 minus 8 gives me 0. So it doesn't matter what the time is. If I have a flat line, my acceleration is 0. So make sure you have that example written down. Okay, the other thing we can do with velocity time graphs is calculating distance and displacement. This is a little different than anything we have been doing with graphs before. And what we're going to do is use the area underneath a graph to calculate the distance or displacement. So remember, area is just kind of a measure of the base times height. So how much area is it covering? So just a reminder, I'm sure you all remember this from math, but just in case, if I'm talking about a rectangle, area is base times height. I want to put these in terms that kind of relate to my graph. So if I'm looking at my graph, I have time as my base, velocity as kind of my height. So rather than writing base times height, I'm going to write velocity times time. So if I have a rectangle, here's my formula. My area or distance is velocity times time. If I have a triangle, I need just one extra step because the area of a triangle is base times height divided by 2. So now if I put that into terms like my graph, I can say the area or the distance for a triangle is velocity times time divided by 2. So make sure you write that down. Okay, one more practice problem here. Let's try this same example. So this is the same graph you saw previously in the video that we calculated acceleration. Now I'm going to take a graph and calculate the total distance. This graph has two different shapes. I have section A and section B. So anytime I have a graph that looks a little bit irregular, I'm going to break it apart into triangles and squares or rectangles. So A is a triangle, so my formula will be V times T divided by 2. So if we look at A, this would be my section A. A has a change in velocity of 8. So the top of mine is at 8, the bottom's at 0. So I can say this is 8 meters per second. The change in time, the base of my triangle is 4 seconds. And then I will divide that by 2. So 8 times 4 divided by 2 gives me 16 meters. So 8 times 4 is 32. 32 divided by 2 is 16, and I end up with a meter. Now for section B right here, it's a rectangle, so I don't need to worry about dividing by 2. And here's my formula. D is V times T. This one has a height of 8 meters per second and a width from 4 to 10. So change from 4 to 10 is 6 seconds. So 8 times 6 gives me 48 meters. So I know this section A is 16 meters, section B is 48 meters, but this question wants the total distance. So I can write that as D with a little t beside it. That means total distance. So to get the total, I'm going to take the area of each of my individual shapes and add them together. In this case, 48 plus 16 gives me 64 meters, and that would be my final answer.